Hello viewers, I am Dr. G. Littleflower, faculty from the Department of Physics, Stella College, Vijayawada. Happy to welcome you all for a talk on Meissner effect, which we come across in superconductivity. What is called Meissner effect? In my earlier video, I have just mentioned about Meissner effect. Today, let us see what is Meissner effect and little bit mathematical expressions for it, and then experimental verification also we will have for Meissner effect. Only then it can be accepted. Meissner in the year 1933 observed that a conducting material, when it is cooled below the critical temperature Tc in a magnetic field, the magnetic lines of force are expelled from it. This effect is called Meissner effect. We know conductors above Tc, they are normal conductors. When they are cooled below the critical temperature, they behave like superconductors. So what are called superconductors? Those which lose their electrical resistance when they are cooled below the critical temperature is called superconductor. Now here what we do is we take a magnetic field. In the magnetic field we cool a conductor to a temperature below the critical temperature. That means when we cool below critical temperature, it becomes a superconductor. So in that state, that specimen begins to expel the magnetic lines of force. This effect is called Meissner effect. So with the help of a figure, it will be very easy for us to understand. So we have chosen a magnetic field B. You could see here. Here we have taken a specimen, a normal conductor we have chosen. So the temperature at this time is greater than this critical temperature. What is critical temperature or transition temperature? It is a temperature at which a conductor becomes a superconductor, right? So when the temperature is above the critical temperature, you can see the magnetic lines of force of the external magnetic field passing through the specimen. That means the specimen is just a conductor only, normal conductor. It allows the magnetic lines of force to pass through it. We have the same situation. Now what we do, we cool this specimen below the critical temperature. So when we cool the specimen in the external magnetic field, it becomes a superconductor. The moment it becomes superconductor, it is not allowing the magnetic lines of force to pass through it. You can see here, when the temperature is above Tc, magnetic lines of force are passing through the specimen. But here, when the temperature is below critical temperature, the magnetic lines of force are not allowed to pass through the specimen. The specimen is expelling the magnetic lines of force. So this is called Meissner effect. This figure A shows a normal conductor in the normal state allowing the magnetic lines of force to pass through. Figure B shows the normal conductor has become a superconductor below the critical temperature and it is expelling the magnetic lines of force. Yes. Now some important points we can find out. First one, Meissner effect is reversible. So you said that when the temperature is greater than critical magnetic field, it is a normal conductor. When it is less than the critical magnetic field, the specimen becomes a superconductor. So this can be reversible. This way we came. It can go this way also. Suppose in the magnetic field, if the temperature of the specimen is increased above the critical temperature, it becomes a normal conductor and allows the magnetic lines of force to pass through it. So we can say that Meissner effect is reversible. from this normal conducting state, we could go to superconducting state by cooling it below the critical temperature. Or you can increase the temperature of the superconducting material above critical temperature so that it becomes a normal conductor and allows the magnetic lines of force to pass through. So we can make a statement that Meissner effect is reversible. Next one, a superconductor is a perfect diamagnetic nature. We know magnetism. Magnetic material can be classified into various types: diamagnet, paramagnet, ferromagnet, ferrimagnet, antiferromagnet, antiferri, and ferrites. So many kinds are there. So here our superconductor behaves like a perfect diamagnetic material. The reason is that magnetic induction B in a superconductor is 0, means the magnetic lines of force are expelled out. So there is no magnetic field inside the specimen. So we say that it is a diamagnetic because only diamagnets can repel. If it is a magnetic nature, it will attract. Only diamagnets will repel the magnetic lines of force. So superconductor is a diamagnetic in nature. So in electricity magnetism, we would have come across a relation connecting magnetic field induction and magnetic field intensity and intensity of magnetization by this relation B equal to mu naught into H plus M. So we say that superconductor is a diamagnet because no magnetic lines of force are allowed to enter in. So B becomes 0. So in this expression, if we keep B equal to 0, then mu naught into H plus M becoming 0. Mu naught cannot be equal to 0 because mu naught is the permeability of the medium. So H plus M becomes 0. We can say M equal to minus H. This is one mathematical relation. So here B stands for magnetic field induction, H stands for magnetizing field intensity, and M is intensity of magnetization. So B is the external magnetic field. So here H tells to what extent that specimen is magnetized. That is what called magnetizing field intensity, and M is intensity of magnetization. Now the magnetic susceptibility is given by, this is another parameter. Magnetic susceptibility is usually given by chi. Chi is equal to M by H. That is, it is the ratio of intensity of magnetization and magnetizing field intensity. Okay. Now, so we have two equations. Equation 1 says M equal to minus H. Equation 2 says chi equal to M by H. So, substitute 1 in this equation 2, M equal to minus H. So, minus H by H gets cancelled and we get chi equal to minus 1. This is the magnetic susceptibility for diamagnetic materials. So, this equation 3 clearly proves that the superconductor is a diamagnetic in nature. So, minus 1 is the maximum value of susceptibility of a diamagnetic material. So, we can say that the superconductor is a diamagnet. Now, mathematically we have proved, right? We picked up some relation and we said that for a diamagnetic material, magnetic field is 0 and we proved that chi equal to minus 1. For diamagnetic materials, the susceptibility is minus 1. Right? Now, in electricity, we have studied 4 equations, del dot B, del dot E, del cross E, del cross B, like that. So, one of the equation, we take up this vector, del vector cross E vector equal to minus dou B by dou T. Okay? Okay? So, the del cross E equal to minus dou B by dou T. Now, according to Ohm's law, all of us know Ohm's law, V equal to I into R. And in electricity, we have studied another basic equation, E equal to V by D. where V is the potential difference between the plates of the capacitor and D is the distance between the plates. So the electric field intensity is equal to V by D. This Ohm's law and this relation are very basic relations in electricity. And we also know that current density J equal to I by A. We define the current density J as the amount of current passing through unit area of cross section of the conductor. Okay. So these three relations we have: V equal to IR, E equal to V by D, and J equal to I by A. Now we take up this relation E equal to V by D. In the place of V, let us substitute V equal to IR. So E equal to IR by D. Now from this relation, I equal to J into A. So in the place of I, now we keep JA into R by D. So this is equal to J, let us take it outside, AR by D. So we have E equal to, in terms of the current density, we define electric field intensity. So E equal to J into AR by D. Now E equal to J rho. E equal to J rho. This is another relation, basic relation, where rho, see here, E equal to, we have got here J into AR by D. So AR by D, we represent it as rho. So this equation can be written as E equal to J into, this factor we are writing it as rho, where rho equal to AR by D. So simply now we are writing E equal to J into rho. The same equation we take, E equal to J into rho. In that expression, if we take J is very finite and rho equal to 0 means E should be equal to 0. Just look at the previous equation. If we say J has some finite value because it is the current density and rho is the electrical resistivity. If rho is 0, E becomes 0. This condition we are going to substitute in equation number 4. Okay. So E becomes, when rho equal to 0, E becomes 0. So in this equation we are going to write del cross E becoming 0. That means minus dou B by dou T becoming equal to 0. That is what we are writing here. Del cross E equal to 0. So when E becomes 0, okay, dou B by dou T equal to 0. So this rate of change of magnetic field induction equal to 0 means B is a constant. Then only dou B by dou T can be equal to 0. These are simple mathematics. So from this expression, dou B by dou T equal to 0 means B should be a constant. Okay. Now you see, this condition of zero resistivity predicts that magnetic field or magnetic flux should remain constant inside the superconducting specimen. So you are a bit confused, right? We just before, a while ago we said what is Meissner effect. According to Meissner effect, a superconducting specimen will expel the magnetic lines of force and there is no magnetic field inside. Under that condition only we derived and proved that chi equal to -1. But from Maxwell's equation, when we derived and applied the basic equations and substitute, we come across a condition called B equal to a constant. So this is just contradiction to Meissner effect. So Maxwell also very great theory, Maxwell's equations, very powerful theory in electrodynamics. And then by using the Maxwell's equation, we find that magnetic flux inside the superconducting specimen should be a constant. But by Meissner effect, magnetic field intensity inside the superconducting specimen should be 0. So these two are contradictory statements. This shows that magnetic flux, so B is constant, means the magnetic flux should not change when the specimen is cooled. So Meissner effect says that when the normal conductor, when it is cooled in the external magnetic field, it becomes a superconductor and expels the magnetic lines of force. So B becoming 0. But from Maxwell's equation, we find that B should be a constant and the magnetic flux B should not change within the specimen. So these two are, this Maxwell's equation result is contradicting Meissner effect. So when we consider superconductors, we should consider both conditions independently. Meissner effect is true and Maxwell's equation result is also true. So this is a great surprise. Even now scientists are not able to explain why, how come we get contradictory results. But both are true. So finally what they say, superconductors should be judged by both conditions independently. If you speak about Meissner effect, you should not bring into context the Maxwell's equation and tell that magnetic field should be constant. If you take up Maxwell's equations and prove that magnetic field induction should be constant, you should not speak about Meissner effect. They both are true. They both should be considered independently. So this is the biggest challenge. We have to find a way to prove that both must be, should not be contradicting. So scientists are working on it. So for a superconductor, let us say finally what is a superconductor? Superconductor has zero resistance below critical temperature. Superconductor shows Meissner effect below critical temperature. So below critical temperature there is no resistance and also it shows Meissner effect. So mathematically we had some simple discussion about Meissner effect. We say that Meissner effect is true and Maxwell's using Maxwell's equation we could show that magnetic field inside the superconducting specimen should be constant. Both are true but we have to consider it independently. Now for Meissner, so finally we conclude that superconductor means it should not have any resistance. Superconductor means it should show Meissner effect. So this is the mathematical way we have come to a conclusion. Now scientific community will not accept it unless it is experimentally verified. So we have to look at some experimental means to verify it. So before taking up the experimental part to prove Meissner effect, let us see what is the difference between a perfect conductor and a perfect superconductor. Perfect conductor and a perfect superconductor. So we know that the susceptibility of noble metals do not change when the temperatures are lowered. So what are called noble metals? Like metals, silver, gold, platinum, iridium, rhodium, all these are some metals which will be very stable and do not get destroyed for a long period, and even in the adverse situations their stability will not be changed. They will be more stable. That is why we go for ornaments made out of gold, silver and all. It will be stable for a longer period of time. Okay, such metals are called noble metals. So what they say, the susceptibility for superconductors, susceptibility is -1 we found. For noble metals, susceptibility, if you study different metals, you take and study by lowering the temperature or increasing the temperature, the value of susceptibility will not change, it will be constant. Not for all noble metals. For each one the susceptibility value will be something, but that value is a constant at all temperatures. That is the thing. Whereas, susceptibility also will not change when the metals become a perfect conductor. Means these metals, if at all they are superconductors, when they become a normal conductor, susceptibility value should not, because when superconductivity is that when the temperature is cooled. So whether it is cooled or whether the temperature is increased, susceptibility value should not change. But in case of superconductors, the susceptibility value changes. When it is a normal conductor, its susceptibility value will be something. When it becomes a superconductor, its susceptibility value will be different. So here we have taken example lead. Lead, we write lead as, we represent lead by Pb, right? So in the normal state, it has a susceptibility of minus 0.12 into 10 power minus 6 normal temperature in the normal state, okay, while its value in the superconducting state is minus 1, the maximum value. So lead when it behaves like a normal conductor, its susceptibility is less, and when it becomes a superconductor, its susceptibility becomes minus 1, still lower than the value of its value in the normal state. Excuse me. I'm sorry. So in this example, lead in the normal state, it has susceptibility, its value is minus 0.12 into 10 power minus 6. In the superconducting state, it is minus 1. So susceptibility of a superconducting state changes, whereas noble metals, their susceptibility, whether you increase the temperature or decrease the temperature, their value will be constant. Therefore, the difference between a perfect conductor and a superconductor is that perfect conductor is only an ideal conductor, while superconductor is an ideal conductor as well as an ideal diamagnet. That is the difference between the perfect conductor and superconductor. Perfect conductor is only an ideal conductor, whereas superconductor, it's an ideal conductor as well as ideal diamagnet. Let us now bring a proof for Meissner effect. The experimental setup is shown here. Here we take a rod made up of superconducting material. We know transformers, primary coil and secondary coil like that. So here, over the superconducting material, we wind up the primary coil like this and connect the primary coil to a battery and a key. We have taken a superconducting rod. Over that, we take a wire and wind it over the superconductor and connect the other two terminals to a battery and a key. Now take another wire and wind over the primary coil on the same superconducting state, because this wire is insulated with paint, so even if they touch each other, there won't be any short circuit. So primary coil is wound over the superconducting rod and connected to the battery and the key. We take another coil and wind over the primary coil on the same superconducting rod, and it is connected to a ballistic galvanometer. So this rod is a superconducting material. It's very simple. We know that Faraday's law, we know whenever there is change in the magnetic flux, it will induce an EMF, right? So suppose if we press the key, the battery begins to supply the current through the primary coil. So when current flows through it, a magnetic field is produced around it. So suddenly magnetic field is represented by magnetic lines of force. So when you close the key, battery supplies current. When current flows through a wire, it produces the magnetic field in terms of magnetic lines of force. So these magnetic lines of force, suddenly there is some change. So far when the key is not closed, okay, there is no magnetic lines of force in the primary. Now when the key is closed, when the current flows, there is generation of magnetic flux, and these there is a change in the magnetic flux, and these flux will be linked to the secondary coil. So according to Faraday's law, whenever there is change in the magnetic flux, it will induce an EMF in the secondary coil. So what happens? The ballistic galvanometer will show a deflection. So ballistic galvanometer will show a deflection only when there is a current. There will be a current only when there is a battery. So here secondary coil, the secondary circuit doesn't have a battery to supply current. Only the primary coil, the circuit, the primary coil part of the circuit is having the battery. So there is current only in the primary circuit. There is no battery in the secondary. But still, the moment you put on the key, you can see ballistic galvanometer shows some deflection. Clear proof of Faraday's law. Whenever changes in the magnetic flux, so when you close the key, current flows, magnetic flux lines suddenly penetrating into the secondary coil. So whenever change takes place, it will induce an EMF. Though there is no battery, it induces a EMF here. That EMF will supply a current in the secondary circuit. So the ballistic galvanometer shows some deflection. I hope you have understood. Right. Now, so the key is now closed. What happened? The moment you close, sudden penetration of magnetic flux, ballistic galvanometer deflected. Now it is continuously closed. So steady current is flowing. Now what happens? There is no deflection. The moment you put on the key, ballistic galvanometer showed deflection. When the key is continuously closed, ballistic galvanometer will not show any deflection. So keep the key closed and make the current to become steady in the primary circuit. Now under this condition, you cool this superconductor below the critical temperature. So the material is superconducting material, right? So what happens? When the current becomes steady, now you have to cool this rod. So when the temperature is becoming less than the critical temperature of this rod, it becomes a superconductor. Immediately what happens? Superconductor means, as per Meissner effect, it should expel the magnetic lines of force. So what happens? Suddenly the magnetic flux lines due to the primary current will be expelled out. Now you can see the ballistic galvanometer showing some deflection, indicating that the flux lines are expelled, and it becomes a direct proof for Meissner effect. So what we do initially, the key is opened, no current flowing through the primary circuit, and ballistic galvanometer will not show any deflection. Now close the key. The moment you close, current begins to flow in the primary coil and produces magnetic flux lines. Sudden penetration of magnetic flux lines in the secondary coil produces some EMF, and it induces some current. Due to that, the ballistic galvanometer shows some deflection. Now when the key is continuously closed, now the ballistic galvanometer will not deflect. Under this situation, you cool this rod over which the primary and the secondary coils are wound. Cool to the temperature which is lesser than the critical temperature. So this rod becomes superconductor now. Above the critical temperature, it is a normal conductor. So when it is cooled below the critical temperature, the rod becomes a superconductor. Superconductor means it is a diamagnet. Diamagnet means it should expel the flux lines which are produced due to the flow of current from the battery. So suddenly it becomes a superconductor and expels the magnetic lines of force. So your BG, ballistic galvanometer, will indicate some deflection. So this time the deflection is confirming that the rod over which the primary and secondary coils are wound has become a superconductor, and it behaves like a diamagnet, and it expels the magnetic lines of force produced by the coil by the current flowing from the battery. So this is a direct proof for the Meissner effect. So this is what written here. Two coils, one primary and the secondary, are wound on a superconductor, actually superconductor, now it behaves like a conductor. It's at normal room temperature. Okay, so the superconductor is above its critical temperature, telling that it is a conductor, normal conductor only. Now in primary circuit there is a battery and the key. Whatever I told you, it is given here, you can read along with me. When the secondary coil is connected to the ballistic galvanometer. When the key is pressed, a current flows through the primary coil. This sets up a magnetic field in the primary coil. The magnetic flux immediately links with the secondary coil. As a result, the ballistic galvanometer shows a momentary deflection. Now, the primary current becomes steady. No current flows in the secondary. So, there is no deflection in the ballistic galvanometer. In this situation, now you cool the conductor very slowly. When its temperature is becoming less than the critical temperature, that the conducting rod becomes a superconductor. So, when it becomes a superconductor, galvanometer shows deflection because in the superconducting state, that rod behaves like a diamagnet and expels the magnetic lines of force produced by the primary current. So, this indicates the flux linkage with the secondary coil has changed. The change in magnetic flux is due to expulsion of magnetic flux from the superconducting material. This is the direct demonstration of Meissner effect. So, it is true that what Meissner has expressed is correct. That is, when a conductor kept in the external magnetic field is cooled to a temperature below than the critical temperature, it becomes a superconductor. In the superconducting state, it behaves like a diamagnet. Diamagnet nature is that it will expel the magnetic lines of force, which is nothing but the Meissner effect. Now, this Meissner effect finds a lot of applications in our daily life. The first one is admiring application is magnetic levitation. So, in Japan and China, we have many maglev trains. Okay. So, in the first part of the picture, let me give some explanation. The lower part, north, means south, north, south, like that it would be there. And here, this is the rails, okay, and here, north, south. So, it will be producing a magnetic flux lines and it will be, the flux lines will be sent above. Now, this is representing the train, the base of which is having superconducting material. Okay, so when you put on the current and send the current to the rail tracks, now aluminum, it is made up of aluminum. So what happens? It will produce a magnetic field, and the magnetic flux will be flowing up. Now the base of the train is having a superconductor. So what will it do? It will be repelling the magnetic flux lines reaching the train. As a result, the train gets lifted up. That is what called levitation from the track a little bit, a few centimeters above. Right? Now what happens? The north pole, suppose superconducting magnet, here also if we take north pole, we know similar poles will repel each other. So due to repulsion, there is levitation coming. The base of the train is having a superconductor. Suppose if we say north pole, suppose we consider only the north pole of the lower, the railway track. So they will repel. Due to the repelling nature, the train will be lifted up. That is what called levitation. Now what happens? The railway track, we will have north pole, south pole, north pole, south pole, like that. We have taken here only the north poles into consideration. Right? Same way, superconductor, any magnet will be having two poles. No monopole magnet is available so far. Even at atomic level, if you go and cut the atom also, one part of it will become north pole and the other part will become a south pole. So, north, south. So, that means it's a diamagnetic superconducting material is at the base of the train. And here on the train track, you have south pole, north pole, south pole, like that. So, now what happens? This north pole getting attracted to the south pole and this south pole getting attracted. Like that, what happens? The train is going forward. So, here we have considered only the north poles. Here we are considering both north poles and south poles. That the superconductor also North Pole, South Pole, and here also North Pole, South Pole. So North Pole of the superconductor getting attracted to the South Pole of the railway track. So it just propels forward. So the train is moving forward and it is not touching the railway track. So it is just floating in the air. So there is no friction. So the train, if it is rolling over the railway track, there is friction and a lot of the speed will be less. As it is floating in the air above the track, no friction, so the train can go very fast. So maybe up to 600 kilometers per hour. In 1 hour, 600 kilometers the train could cross. So this is very successfully in Japan and China it is going. They are using maglev vehicles. This is one of the application. And the next, many applications are there. I am just mentioning one or two. So next one, the superconductors provide good magnetic shielding. There are some electronic instruments. There are some experiments which we have to perform in the absence of the external magnetic field. So in such a situation, if we keep some superconducting magnet around the electronic instrument, that superconducting shield will repel the external magnetic field. So the electronic equipment will be isolated and you can do the experiment so precisely and find out without any external magnetic field interference. Thus superconducting magnets, superconductors can provide magnetic shielding. Especially it is useful in particle accelerators where for example the CERN lab is doing this particle accelerators where protons will be accelerated in opposite direction. When they collide with each other, huge amount of energy will be produced. So that energy can be utilized for electrical generations and all. So superconductors are used in the particle accelerators and also in the magnetic resonance imaging machines in the medical field. Nowadays we don't prefer to take X-rays or CT angiograms and all because we are exposed to high intense X-rays which will be dangerous in the course of time. So nowadays doctors prefer to use MRI, magnetic resonance imaging, and they can know the nature of the internal organs and diagnose the disease. Okay, so thus this superconductors are very helpful to make accurate readings. And some more applications, superconducting sensors are there. Okay, these sensors will detect very small magnetic fields also with high precision. Very minute magnetic lines of force coming also, these sensors will sense to greater precision. So they found applications in various fields including medical diagnostics, material sciences and security systems. Okay, security systems. And then we have SQUIDs, superconducting quantum interference devices for a medical imaging. For example, magnetoencephalography, that means to monitor the brain activity. They use a squid ring around the head and study whether any changes in the magnetic field. Okay, geology also they use, and fundamental physics research. Thus, superconductors find so many. I have just narrated a few only. So many applications are there. We can read from the books or from internet. So it's such a lovely topic. I hope you all enjoyed. I thank you one and all for listening to me. We will meet soon again with another topic in physics. Thank you.